If our parameter w is a multidimensional vector, not just a univariate parameter, we can take derivative with respect to each one of them. Suppose we have m parameters, and then we stack all those derivatives together. That's the partial derivative. It is a vector of m dimension. Then the gradient descent will perform similarly. The recurse formula will be the current value of w, which is a p-dimensional vector, minus the this learning rate, a small positive number, times the partial derivative, another m-dimensional m-dimensional vector. Of course, now due to multidimensionality, there's a bit more challenging with this algorithm. Common issue would be oscillation, and also how we're going to adapt to different dimensions, assuming the different dimension of the features could have different scale. So there are tons of methods available. How to improve the efficiency of gradient descent in a high-dimensional setting is still a very active research area in machine learning. And nice thing about this area is you don't need to code this by yourself. For example, in Keras, you just pick one of the optimizer, and as a beginner, if you really don't know the difference of those algorithms, just pick one of them. That will work. Let me just say a little bit about this oscillation. So here is a picture you probably you will see in a lot of lecture on gradient descent. You can think about your here. This is a contour plot for a two-dimensional parameter w, and at every location, the gradient is basically the direction orthogonal to the tangent over this contour plot. When the contour plot is not circle but ellipsoid, then there's some kind of a correlation among those of the two. Not correlation, but the two dimension will behave differently. You can see this oscillation effect. You can see in the vertical direction, the gradient kind of keep changing direction. Signs, you go sort of a forward, back. But along the horizontal direction, it's always moving this way. So to reduce oscillation, people have studied a lot of methods. They all try to learn something from the history of the gradient, instead of every time just find a new gradient vector. For example, the intuition here is if you could do some kind of weighted average at each point, if you can do a weighted average of the prior derivatives you've calculated, you can imagine the oscillation along the vertical direction can be cancelled out because they're positive, negative. And the remaining direction will sort of more move faster along the horizontal line, which is exactly what you want, like this. So for those new algorithms, the gradient descent formula may not be exactly like this, not just a simple learning rate times a partial derivative, but the formula you don't really need to code those. You can just this already being built in those optimizer functions. Another thing you're going to encounter when we move to neural network is the so-called chain rule for gradient. So here, let's just go back to the one-dimensional case because it's easier to write down here. So if the objective function is a function of w, but suppose you can write it as a function of z, and z is actually equal to another function of w. So in some sense, you can think about f is like a g parenthesis hw, or I can think this way. And so then the gradient of f with respect to w is equal to the product of g respect to z and z or h respect to w, just a simple product. And the reason why we wanted to write in this way, just because it's possible the derivative of g respect to z and also the derivative of h respect to w, and they are much easier to compute than the original derivative respect to of f respect to w. We actually encountered this when we derive the MLE for logistic regression. And I don't mean to ask you to kind of understand all the formula on this slide. This slide is from our from our lecture notes for logistic regression, so you can go back to take a look of the MLE for logistic regression. You can see here we can take derivative of sigma versus z and z versus beta, and just do a simple product. Okay, so we have discussed the how to pick an optimizer. There are some nice scenarios, but if your objective function is really complicated, at least you can always go to gradient descent. It is not ideal, but at least is a method you can just is better than nothing. So you can still find a solution better than your initial value. What about choices for loss functions? It depends on we're working with a regression problem or classification problem, and the loss function may be different. For example, we've encountered L2 loss for regression, and for classification we used log loss or entropy loss when we work with logistic regression, and for SVM we use hinge loss. And when we talk about boosting, we also talk about exponential loss when we describe the boosting algorithm. So there on these two places you can look at the available loss functions and also metrics. Sometimes we differentiate loss function and metrics, because sometimes the loss function needs to be chosen for mathematical convenience, because we want to be able to calculate derivative. But metrics, for example, like L01 loss or AUC, those are like the ultimate metric we aim to minimize, but the underlying function might be mathematically unfriendly. So we wouldn't use as a loss function, but we can still use it as a metric when we evaluate the final performance on a test data. So in Keras, they differentiate this two. You're going to see almost all the loss functions are also listed as a metric, but not vice versa. So what about the last item, function space? We have already know there's a limitation with the linear functions, although it's easier to work with. So in this semester, we have tried different approaches to move beyond linear function space. And let's see what we have tried. In one-dimensional case, we talk about polynomial regression. Of course, we don't want to work with a polynomial function with a large d, because the function may fluctuate too much and in the boundary region, and also it's difficult to interpret. So we move to splines. We basically divide the interval into small intervals, divide the range of x into small intervals. And within each interval, it is a nice cubic polynomial function. And then we add constraints when the two intervals meet each other, because at that middle point, and that middle point is defined by two different polynomials. We want to make sure and the two definitions, the two polynomials are continuous up to a certain degree of a derivative at that point. It turns out under those restrictions, it is still a nice function space to work with. We have basis functions, so we can talk about regression spline models or smoothing spline models where we want to add an L2 penalty. Another extension is local polynomial regression, like the Loess model, which basically model the function and kind of locally at every single point x. It is going to be a polynomial function, maybe cubic or quadratic, and the coefficients sort of smoothly change at every location, but they're not exactly the same. And so all those may be able to extend to a moderate dimension like p is 2 or 3, but usually when dimension p gets larger, all those nonlinear models will work with one dimension case won't be able to move to high dimensional case because the curse of dimensionality. The number of parameters will grow exponentially fast. And so as a compromise, we discuss the additive model, where we assume the function we aim to estimate over a p-dimensional feature is actually a summation over one-dimensional nonlinear function, and each one is a nonlinear function of a particular dimension, a particular feature. So of course there is a drawback. The price we pay is we totally ignore the interactions among the p covariates. But this is sort of a compromise we have to make due to computation purpose and also even interpretation. What else we have tried? And we also talked about SVM, where we introduce a kernel function, and then the function we wanted to estimate can be viewed as a linear combination of those kernel functions with one argument fixed at the data point. And we also talk about tree models and also how to combine them through either bootstrap aggregation or boosting. So that's sort of a model ensemble. What else we have tried? There is another approach, very heuristic. I don't think I ever formally described it in class, but I've seen this being used in practice. It's called a model stacking. For example, we can fit a tree model, we can fit a polynomial regression, we can fit a additive model, or maybe another regression with a lasso. So you can fit a bunch of models. And here we have fit 3 models. And then you're going to take the output from those models as a new feature for a linear regression model. So you threw their output into another linear regression model, and you learn their coefficients. Or you can even throw them into another random forest or XGBoost. So this is called the model stacking, and in the sense that we just stack those models, from top to bottom. The output from the model on the prior layer is going to be input for the model in the second layer. Very heuristic, but that is really related with very much related with this idea of neural network. So here's a simple one hidden layer neural network. In this case, we have a 3-dimensional input, x1, x2, and x3, and then they're going to go through some model and going to generate 4 hidden outputs, so 4-dimensional hidden outputs. And those 4-dimensional hidden outputs then going to go through another layer and give me 2-dimensional output. So how they go from one layer to another layer, it is actually just a simple linear regression model with an activation function. So for example, let's see how we're going to get the hidden layer, and we have 4 hidden layer outputs. So it's H1, H2, H3, H4. So for example, how we get H1, we get a linear combination of the 3 inputs, and those 3 edges, each one of them going to be attached with a weight. So it's W1, W12, W13. And then there's a intercept C. And sometimes they call it Bayes term, but the Bayes here is basically intercept. It's nothing negative. So for this hidden layer, we receive a linear combination of the input from the 3 input plus an intercept effect. That's what's the outcome in this parenthesis. And then we're going to apply a nonlinear transformation known as the activation function, which is sigma. So in the old days, the sigma is basically a step function. So whatever inside this is bigger than 0, you output 1, otherwise it's 0. Of course, we know there's going to be a problem because the step function is not continuous. So people move to a more continuous approximation of the step function, which is a sigmoid. But nowadays, more of the state of the art is so-called the ReLU, which is 0, and then you just only allow the positive information get passed to the next layer. So that's how you get your hidden layer. Now, once you get your 4 hidden layer out and values, H1, H2, H3, H4, again, you can go through a linear combination, but only linear combination, no activation function anymore. So you can get the output, which is a linear combination of those 4 hidden layer and plus an intercept or Bayes term. So let's look at what are the parameters here. So we're going to count the number of parameters. So for this model, we can count the number of parameters from one layer to the next layer. So from layer J to layer J plus 1. So, and it's always equal to the number of layer from the length of the prior layer, the input layer, plus 1, and times the number of layer at the next level. Well, this is because you have, for every node in the next layer, it receives a weighted, it needs a coefficient of the length of the prior layer, but plus an intercept. So for example, in this case, from input layer to hidden layer is 4 times 3 plus 1, so it's 16. Now from hidden layer to output layer, and it's 2 times 4 plus 1 is 10. Okay, so that's how we count the number of parameters in this simple neural network. So let's take a look of the simple example of a neural network. In this case, we have our input dimension is 2-dimensional, and our hidden layer is also 2-dimensional, and the final output is just 1-dimensional. And so we've given the parameters W from the red to blue. Those are the 2x2 matrix or 2x1 Bayes vector or intercept. And from the blue to final output is 2-dimensional coefficient plus the intercept. Here the intercept is actually 0. And we're going to use a ReLU activation function. So here's the formula for what the input vector x1, x2 go through all this and eventually get a final output y. So let's calculate what if my input 2-dimensional vector are those 4 points. You're going to find out the output y, and is going to, you have the same value on this diagonal 2 points and same value here. So that's sort of XOR configuration, and we know linear function won't be able to achieve this outcome. And so this simple neural network actually is a defining a nonlinear mapping can give us this XOR configuration. So let's work with, just go through this calculation. You can pause the video and just do the calculation by yourself. Let's first look at what if our input is 0, 0, so this point, okay? And so we just plug in this formula, and you can do the calculation. So inside the parentheses, the wx plus c, you get this vector, this outcome 0, minus 1. But then once you apply the ReLU activation, because only positive can go through this activation, so you get actually 0, 0, because minus 1 just gets suppressed. And then once you get 0, 0, and when you do a linear combination of small w and also at the location shift to 0, you still get 0. So you can also work with the output if your input is 1, 1. Similar, you're going to get 0. So you can pause the video and work with the other two inputs. You can get -1 and -1. And so this is a very simple example of neural network, and we have only one hidden layer. But nowadays people build neural network of many hidden layers, and in terms of the depth is large, so it's often called the DNN, deep neural networks. So for example, this is a simple one, but you can add more hidden layers. So now if you want to use neural network to do supervised learning, you have a similar flow chart. You're going to collect data first, and then instead of pick a function space, and you're basically going to use neural network. So you're going to pick a network architecture, and like how many hidden layers, and how many hidden nodes in each hidden layer, and you can even talk about how those layers are connected to each other. It depends on, are you talking about convolutional network or RNN, and which I'll show you some examples. But once you pick a network architecture, and the remaining two is actually similar to the other, similar to the flow chart we encountered before. You pick a loss function, and you're going to pick a optimizer. Now, because of the network is that kind of loss function is not the loss function. Actually, the function space is much more complicated than just simple linear function or polynomial, where we exactly see where the coefficients are. The derivatives in neural network, they are sort of buried into layers. So the ordinary like you cannot expect there's going to be a closed form. So the go-to method is just gradient descent, and so that's usually what people use for when they pick an optimizer, just a gradient descent. But for neural network, even the gradient calculation could be challenging. So let's take a look at how the chain rule will be used to calculate gradient when you work with a neural network, and the resulting algorithm often referred to as the back propagation. So here's the picture of that simple one hidden layer neural network I showed you before. 3-dimensional input and 2-dimensional output, and we have 4 hidden layers. And so here's the expression we had before. Now the parameters are all those weights attached to each of the edge, and also the bias or intercept vector. So let's look at how we're going to take a derivative respect to the weight here, which is the lowercase w. So you're going to take, for example, w11, you just take derivative of y1 respect to this w11, and the dependence between y and this lowercase w is just basically a linear model. So this can be calculated pretty easily. Even for b, I didn't list it here, but it's not difficult to compute. Now, how we compute the derivative respect to the weights attached to the connection between the input to the hidden layer. So it's a bit far away from the y, and that's where you're going to use the chain rule, because let's see how w11 is related with y. So this one is related with h, and we can even think about the whole expression as a linear combination inside the parenthesis of sigma as z1. Okay, so h1 is equal to sigma times z1. Z1 is whatever inside. So the connection between, or the dependence relationship between z1 and this w is very easy to compute, because it's just a linear function. So this is where, and then we can talk about how h1 depends on this z1, and then we can talk about how y depends on h1. So let's put all this together. When we take derivative of y1 respect to this weight, we use chain rule. So because the W11 respect to y through z1, h1, and this. So it's derivative of y1 respect to h1, h1 respect to z1, z1 respect to w11. And for those two, if you can pause the video, think about this derivative and this derivative, the underlying dependence is a linear function, so it's pretty easy to compute. Now from h1 to z1 is basically the derivative of a sigma function respect to its argument. If you use ReLU or even sigmoid, that's pretty easy to compute. So we can calculate derivative of y, the outcome respect to all those, the weights on the layers, which is a bit far away from y. So it's doable. But you might be wondering, well, how about if we have multiple hidden layers? And the same chain rule method can be used. However, we encounter another issue. So for example, let's look at this case where we wanted to take derivative of this outcome respect to this particular weight, right? We can use chain rule and try to figure out what is the derivative respect to this particular node, and then this particular node respect to this weight. But to compute the derivative of this outcome respect to this node, we have to go through all the other, almost every nodes in the prior layers. Oh, by the way, there should be an edge, I think. I don't know why they didn't put it here. So basically, to compute the derivative of this outcome, this blue node to this orange internal node, you have to sum over the derivative over all possible paths, like this one here, 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 here. So you have to sum all over all the possible paths from this blue one to this orange node. So there's a lot of summation going on. Now, it's even worse if next you're going to talk about, well, you're going to take for example, in this case, you're going to find out all the calculation is kind of related to the derivative from this blue node to this orange node. And similarly, you're going to compute the derivative of this blue node to this red node. I mean, this orange node marked with red star. Again, you have to go through all those paths from those to this one. So the computation, there's a lot of computation because when you're going through all the possible paths, it's like we expect it's going to be exponentially many. Now, even another issue you suddenly realize is there's a lot of redundancy because all those paths you have to kind of recompute. You can see that redundancy already here, actually. You can see here when we take derivative of y1 respect to this different weight, you can see the first two actually are the same. So you're going to encounter this, first you're going to realize there's a lot of calculation you need to do, and some of them are redundant. And I don't know whether you still remember how we compute the forward and backward probabilities for hidden Markov model. Back in the middle of the semester, again we encounter something very similar because we have to sum over all the possible value for the hidden nodes, those z's. And again, we sort of expect an exponentially increase in computation cost. But turns out there's some trick we can use to reduce it computation. And basically, at every time, for example, we can compute the derivative from the blue node to all the hidden orange nodes here and save them. Now, when we calculate the derivative from this orange node to this node, we just collect all the information here. And now let's look at, for example, suppose at this orange node, we already saved all the derivative from orange to this one, no matter what the middle node you've gone through, but this node now save all possible paths going from the blue to this orange. Then when you compute the derivative of this blue to this particular node, you just collect derivative information only from this layer because it's already saved, because you don't need to worry about all the prior layers. So in short, there is a clever way you can save the computation such that when you calculate the derivative, you're going further back in this network, you only collect information from prior layer. So the computation cost is essentially linearly in terms of the length of the network, not exponentially. And the trick is very similar to that hidden Markov model trick. And that algorithm is basically the backpropagation algorithm. So you have to, actually you can see the backpropagation and description here. Because when you do your calculation, you can see you can, going backward, compute all the derivative. But then once you get the derivative, you know the update. So you have to go a forward step to update all the weights, and then go backward again to do the derivative, and forward again. So every backpropagation actually involves 2 steps, backward and forward. And you recursively and do that. So that's basically the deep neural network. You pick a network architecture, and you pick a loss function, pick an optimizer, and those 2 steps, and the Keras, a lot of packages, for example, I'm going to show you with Keras, they already have some, you don't really need to write down those details. The tools are available. Now, even for network architecture, it's like you're playing a Lego. So you just put things on top of each other, and so the grammar-wise is very simple, and then you just use gradient descent to find a solution, and then you can do your prediction in the future. So I'm going to show you how to use this in R and in a different video.